All right, so we're going to finish up 5.4. So we're going to do a little bit more with logarithms, okay, starting with just looking over some properties for exponents. And then we're going to do something on the calculator that we haven't done before. So we're going to learn something new. Okay. So the first problem they want us to do is rewrite that expression just without negative exponents and without numbers in front of any of the variables. So a to the x, a to the y, and a to the z. Okay, right now we have a 2x, a 3y, and a negative z. All right, so what we want to think about is how we would have gotten to this point. If you are adding two things together to get an exponent, what would you have had, or can someone give me an example of when you would add two numbers together and put the answer in the exponent? Okay.
When you multiply.
Okay, so give me like a not maybe even with that. Just give me an example with all numbers.
Let's say 2 to the second times 2 to the third would be equal to 2 to the fifth.
Right. Okay, so using the property, when you multiply things with the same base, you would add the exponents. And when would you subtract an exponent? When does that happen? Yeah.
Would you write it?
Okay, can you give me an example of that?
So 2 to the fourth.
Let's see something besides 2.
4 to the seventh.
Okay, yeah.
Divided by 4 to the third.
Yeah. So 4 to the 7th divided by 4 to the 3rd. When you simplify that, you would subtract because it has division. So now let's apply those two rules to that problem and see if we can kind of work backwards to how we would have gotten that. All right, so let's start with a to the 2x plus 3y. What would you have had before you got to that step? Yeah.
A to the 2x times a to the 3y.
Times a to the 3y. Yeah. And now, if you have a minus z, what would have given you a minus z? Yeah.
Division.
Division. And what would you have divided by?
A to the power z.
A to the power of z. Okay, so we got rid of the negative in front of the z, and we have one of the things that they asked for. Okay, rewrite it in terms of a to the z. Okay, we've got that. Now we've got to fix a to the 2x and a to the 3y. This is another rule. How would you have ended up with a product in the exponent? Can someone give me just a simple example with numbers? That you would multiply two things together, and that would go in the exponent. Yeah?
A to the x times a to the x, for example, to get a to the 2x.
Can you give me an example with all numbers?
X.
That's a letter.
2.
We like twos. Okay?
2 plus 2. 2 times 2.
So we could start with 2, but how would we end up with something where we have to multiply two things together and put the answer in the exponent? Yeah?
2 to the 4th, and then raise multiplying to, I don't know, the 6th.
Sure. So that would be 2 to the 4 times 6. Okay, so there's 3 very basic rules we learned in Algebra 1. We're just applying some of those now to this problem, and it has variables. So let's start with a to the 2x. How could you rewrite a to the 2x in terms of a to the x? What could you do with a to the x to turn it into a to the 2x? Yep.
A to the x to the 2.
Perfect. A to the x squared. So now we've rewritten the original problem in terms of an a to the x. We're going to square a to the x. How about a to the 3y? How could you rewrite a to the 3y in terms of a to the y? Yeah. So now we have a, oops, 9. a to the y cubed divided by a to the z. So it's just practicing manipulating an expression using rules of exponents. Any question on how we turned that into that? Okay, so that's the first thing. So that's rules of exponents. The next thing we're going to look at is how we can solve some of the problems we've already done, like about exponential growth and decay. But now we're going to do it algebraically. We've done this exact problem with these exact numbers already. I think we did it on maybe Tuesday. So we had a town with 50,000 people. The population was increasing at 2.5% every year. And they wanted us to figure out how long it'll take for the population to reach 100,000 people. Well, regardless if we're going to solve it graphically or algebraically, we need an equation. First thing is to determine, is this exponential growth or decay? Yeah, this is growth. So let's write down the formula for exponential growth. So let's do population as a function of the time that has gone by. What's the first thing that comes after the equal sign in the exponential growth formula? In general, you don't have to give me a number yet. I just kind of want to know in general what comes after it. Yeah?
P.
Which is
population.
Yeah, it's the initial value. Okay, whether it's an amount of bacteria, an amount of money, whatever it is, it's whatever you're starting with. Now I want the actual value, which would be
50,000.
50,000. All right. Then in parentheses after that, what do we put? Just in general. Yep. 1 plus r. So now in this problem, we got to look up what r is. So we've got 1 plus, and what's going to come after the plus sign? Yep. Yes, 0.025, because you have to change that percent to a decimal. Okay, so 0.025. And there's one more thing we need. Without this, it's not an exponential equation. That's the last thing I need. Yep. T as my exponent. All right. So let's simplify that a little bit. So P of T equals 50,000 times 1.025 to the T. Okay, and now they want us to figure out when the population reaches 100,000. All right, so we have two choices where you plug that in. You're either going to plug in 100,000 here, or you're going to plug in 100,000 there. In this problem, what is the 100,000? Is it a population, or is it a time? Yep.
It's going to be a population, so you plug it in for P of T.
Right, it's population, so we're going to plug it in for P of T. So take that 100,000 and put that in right there. And this is about what we got to last time when we solved this graphically. I think we did one more thing after this. So now we're trying to get T by itself, and we're trying to do it algebraically. What could I do on both sides? At least it would make numbers a little smaller. It still doesn't get T by itself, but we did this graphing it too. Yeah.
Divide by 50,000.
Right, we can divide each side by 50,000. So 100,000 divided by 50,000 gives me 2 equals 1.025 to the T. Okay. Any questions on that so far? All right. Now, the reason we wouldn't see something like that in Algebra 1 is because you have a variable, and it's in the exponent. It's a variable that's in the exponent. So that's an exponential equation. what could I try to do with that? Instead of writing it as a exponential equation. Yep. Right, we could try making it a log equation and see if that helps. So let's start with log. What's going to be the base on my log? Yeah. 1.025. All right. And logarithm always equals what kind of number? Yeah. Logarithm always equals the exponent. And where would my argument go now? Yeah. Yeah, after the log. That's my argument is what was by itself, too. So we have an answer. T is equal to this. Got T by itself. But what's the problem with that as of right now? Like, let's say I want the number. What don't we know yet? Yeah?
How to plug it into a calculator?
Yeah, we don't know how to plug in something that's base 1.025. We know how to plug in two different bases. Can someone remind me, what's one base we know the calculator can do? Yeah?
Base 10.
The calculator can do a base 10. And which button do you press to do base 10?
Log.
Log. So that's your base 10. And what's the other base the calculator can do? Just pressing a single button. Yep. E. And what button do you press to do base E? Yeah, just ln. Okay? So those are the two bases the calculator can do without knowing anything else, base 10 and base E. That's not base 10 or base E. So I'm going to have to come back to that once I show you how you type that in. But basically, that is our answer. All right, so we'll come back to that as soon as we know how to finish that up. Okay. So we ended up with something that is our answer. We just don't know how to type it in yet. So I'm going to show you a property of logarithms that's going to help you figure out how to type that in on a calculator. And not just a graphing calculator, but any calculator, as long as it has a log button, right? You can type that in on. So let's look at these properties. There's three properties we're going to look at. The first two we are going to use, but they're not going to directly help us to answer the question we're doing right now. I want to start with the first two, and then we'll get to the third one. So the first property of logarithms has to do with the logarithm of a product. If you have the log of a product in your argument, you can separate that into two different logarithms. Okay, kind of break it down. When you break it down into two logarithms, each log has the same base as the one you started with. The first argument is the first factor, and the second argument is the second factor. Now, you can do that with more than just two. Like if you had x times y times z, if you were multiplying three things right here, you could separate it into three logs. The key is multiplication in the argument turns into addition if you want to split it up. So here's an example with numbers. Okay, if I type in log of 20, which is 4 times 5, okay, or I do log 4 plus log 5. Well, if you do plus, it'll work, not if you do minus. You get exactly the same thing. Okay, so log of 20 is the same as log 4 plus log 5. Based on that idea, anyone think they could give me a different way to type in log 20 besides log 4 plus log 5?
2 plus log 10.
Yep, log 2 plus log 10. Right, any two things that multiply to give you 20, if you split it up with that formula, it's going to come out the same. And now, I said here, the base can be anything. What base am I demonstrating it with on the calculator though? Yeah?
Base 10.
Right, I'm demonstrating it with base 10. I could have done base E. That's the only one we would know how to, other one we would know right now, but it does work for any base. The key is just keep the base the same. Whatever you started with, that's what you split it up into. All right. What about, instead of a product, a quotient? How do you think a quotient would split up? Yeah.
You subtract.
Yeah, a quotient is going to split up into subtracting two logs. The key here, though, is because it is subtraction, the order matters. So it's always the log of the numerator minus the log of the denominator. With the addition, it doesn't matter as much because addition is commutative, but subtraction is not. So log of 4/5 would be log 4 minus log 5. Now, both of those properties, they're useful. It doesn't help us to still answer that question, though. But we are going to practice these properties. The third property is what's going to help us to answer how we type this in on a calculator.
Log over log.
So let's look at this one. This says log base A, and then the argument is m to the r. When you have an exponent on a logarithm, you can take that exponent and put it in front. So here's an example. And rule 3 is really like rule 1. They're very similar. Let me show you why. Right, let's do this one. Right, but let's rewrite it. Instead of log base 10 of 3 to the 5th, what does 3 to the 5th mean? If I were to write that out the long way. What's 3 to the 5th? Yeah. Yeah, it's 3 times 3, 5 times. So let's do 3 times 3 times 3 times 3 times 3. Everyone agree that's what 3 to the 5th means? Okay. So now, what you have here is a product of 5 things inside parentheses. When we have a product of things we are multiplying together, a product turns into what when we split it apart? Yeah. A product turns into addition. Yeah, turns into addition with however many things you're multiplying together. So, how many things are we multiplying together there in my argument? Nick? 5. So if we split that up using rule 1, we're going to be adding 5 things together. When I split it up into 5 different logs, what's going to be the base on each log? Yeah.
10.
10. It's going to be the same base that I started with. So log base 10, log base 10, log base 10, base 10. Okay, so we split it up into 5 logs. They're all going to be added together. And what's going to be the argument on my first logarithm? Yeah, 3. That's that one. What's going to be the argument on all my logarithms?
3.
3. It's going to be the second one, the third one, the fourth one, and the fifth one. So it's really just rule 1, where you have the same numbers inside over and over. So now look at what we have here. We have log base 10 of 3, and we have how many log base 10 of 3s? Yep, we have 5 of them. So if you add them all together, you're adding 5 of the same thing. So if you did x plus x 5 times, you'd call it 5x. When you add 5 of those together, it's 5 of the log base 10 of 3s. That's why the short way to think about it is the exponent ends up moving in front. Now, the other thing we've got to be careful with is sometimes they may say in a problem, rewrite your answer without any exponents on the argument. So that'd be an example of doing that. This has an exponent on the argument. This does not. If you wrote that as a final answer, and I said not to leave exponents on the argument, you've left an exponent on that argument. Right? It's hidden, but you left an exponent there. And we talked about this when we did radicals. The square root of x is the same as what?
X to the 1/2.
That's really x to the 1/2 power. So if you were going to rewrite something like that, and I said no exponents, how would you fix this so it doesn't have even a hidden exponent? Yep.
Be 1/2 log x.
Yes. So this is really x to the 1/2 power, and that 1/2 can move in front. Because anytime you have an exponent on an argument, it can go in front. And so that's important, and that's something that sometimes people get tripped up on. When they see a root in the argument, they forget that that's really an exponent. All right.
I was going to say there's one more.
There's what?
There's one more.
There's one more?
Yeah.
What is one more?
It's that log base m equals log m over log base.
Oh, okay. I think you're talking about like the change of base formula.
Yeah.
We're going to talk about that one in a certain amount of time.
Okay.
Not sure if it's today or not, but yes.
I was going to say.
Yep, very good. All right, let's just try a few of these. Okay, practicing with those, and then we're going to come back to that and see if we can figure that out. All right, so this says to separate into multiple logs, express powers as factors. Okay? Essentially, when you see express powers as factors, that means do not leave exponents in the final answer. That means put them in front. If the problem has an exponent. If it doesn't, then that second sentence doesn't apply. Okay, so we're going to split that into multiple logarithms. How many logarithms is that going to split up into? Yep.
3.
How many things are you multiplying together in your argument?
2.
2. Okay, so that's going to split up into 2 logs. Log, log. What's going to be the base on each log? Yes?
4.
4. Good. So 4 will be the base on each log. Are we going to be adding these 2 logs together or subtracting them? Yeah.
Adding.
We're adding because that's a product. Product turns into addition. What's the argument of my first log? Yeah.
3.
3. And how about Dex? What's the argument on my second log?
X.
Yeah, perfect, X. And that's all you can do. That's how you split that up into 2 different logs. A lot of times we prefer to combine logs together, so we want to do the reverse of this, which we'll practice that too. But sometimes we need to split them up. Just, I guess it depends on the problem. All right, let's try this one. Izzy, how many logs is that going to split up into?
2?
Yep, it's going to split up into 2 logs. What's going to be the base on each log?
I don't know.
What's the base on the log that you started with? No, 5's not the base there. That's on the line with everything else.
2?
2. How do you know that?
There's a 2 there? I don't know.
Because what?
There's a 2 there?
There is a 2 there. There's also a 5 and a 3 there. Someone tell me, why is the 2 the base? Why not the 5 or the 3 or the other? Yep.
Because the 2 is the subscript of
Right.
1.
You look for the subscript. So the number that's the subscript, that is your base. So that's going to be the base on each log. Are we adding or subtracting these logs? Jack, are we adding or subtracting them?
We're adding.
Yeah, we're adding them because we have a product. Moises, what's going to be the argument on my first log? 5. And Ryan, the argument on my second log?
It's gonna be 5.
Well, what's my second factor? Let's start with that. In the argument, what's my second factor? It's what?
Is it 3?
No, so first factor, second factor. So my second factor is r cubed. Okay. What's going to happen though to that r cubed? Because it says express powers as factors. So if we leave it as r cubed, that's not going to be right. What can we do with powers when we have a log? So look at rule 3. So what does it say happens to the exponent in rule 3? Think about when I had that log base 10 of 3 to the 5th and we rewrote it, what happened to the 5 in that? So when we had log base 10 of 3 to the 5th, we put equals, and what was on the other side of the equals?
It's 5.
5. So it was 5 log base 10 3. So we had that whole thing. So what happened to the exponent in that problem?
It went to the front.
It went to the front. So normally the argument here would be r cubed, but what's going to happen to the 3?
It's going to go to the front.
It's going to go to the front. Yep. So what would be in front of this log base 2?
3.
3. And then what would my argument be?
R.
Yeah, exactly. Okay, so that's the final answer. So the 3 goes in front, and you have log base 2 of 5 plus 3 log base 2 of r. Any question on that one? Yeah?
Are these properties related to the properties of square roots or no?
This particular problem doesn't really have anything to do with
No, I mean like
roots.
the properties of logarithms. Are they related?
Properties of logarithms? Yeah, we're using these 3 properties
Yeah.
specifically.
Are they related to square root properties though too?
The only time that a square root really comes in is like if you have an exponent that's a fraction, specifically like a 1/2. That would be a square root.
Okay.
Yeah. These particular problems, no, they're not related to square roots. No. Let's look at this one. Log base 9 of x divided by 2. Okay. we're going to split that up. Cecilia, how many logs is that going to split up into?
2.
Yep, so we're going to have 2. What's going to be the base on each log?
9.
9. 9. Are we going to be adding the 2 logs, or are we going to be subtracting them? Which one? Yeah.
Subtract.
Yeah, we're going to subtract them because it's division. Okay, so big difference there. We're subtracting the 2 logs. What's going to be the argument for my first log? Yep. Yep. So the argument is the first argument is the numerator, and my second log is going to have an argument of 2. And that's how you'd split that up into 2 logs. All right, let's try this one. Now, we did it with log base 4, log base 2, log base 9. What are we using for a base now? Yeah, E. Right? It works. These properties work for any base. A can be any positive real number. Right? Now, we're not going to write log base E. We're still going to write ln. We're going to use the abbreviation. But anyone think they can split that up and give me the final answer? Yeah?
It's going to be 3 ln y of y minus ln of 8.
Yep. So it splits as subtraction because it's division. And the first argument would be y cubed, but that 3 needs to go in front because they said to do that in the directions. Exactly. Okay. Any questions on that one? All right. Just jump to this one. So this one, it's got a lot of stuff going on. It's got exponents, it's got products, it's got division. It's going to have every rule in it. Okay, so now I'm combining them all together. Okay, the first thing you want to do when you look at a problem like this, if it looks like there's a lot going on, then just think of it like that. It's the log of something over something. Deal with that first. When you have the log of something divided by something, how is that going to split up? Yep.
It's going to be the log of A minus whatever.
Mm-hmm.
Minus log A something else.
Yeah. So it's going to split up into a subtraction problem. Now we need to look at actually what is in the numerator and denominator, and then that might simplify even further. Okay, but it's going to split up into log A minus log A. Now let's look at what we actually have. Put the top down as your first argument. So square root x squared plus 1. And then put the bottom, put that down as the second argument. X cubed times x plus 1 to the 4th. Okay, there's not a lot we can do with the first one. There's only one more thing. How can I simplify this so it no longer has an exponent, even if it is a hidden exponent? Yep.
Change it to 1/2.
So yeah, 1/2, and then what would come after it?
And then log A x plus squared plus 1.
Yep. And we want to keep that x squared plus 1 in parentheses, because if you don't, then it gets confusing if the plus 1 is actually part of the log, or is it really meant to be a plus 1 like on the outside? Right. So just keep it all in parentheses. All right. Now let's look at the second one. Minus, and we're going to do something to that second one. If you get confused and there's a lot going on there, try to break it down and just think of it like this. It's the log of something times something. I need to worry about what those are in a minute, but for now, it's just something times something. How does the log of a product split apart?
It's log A plus log A something.
Right. When we split that apart, it's going to split apart into a sum of two things. Rectangle 1 and rectangle 2. Log base A, log base A. Now, let's look at what those are and see if we can go a little further. Okay, the first one is x cubed. That's a hint. So what's going to happen to x cubed when I rewrite it down below? Yep.
It's going to turn into 3 log A x.
3 log base A of x. So we dealt with the first one. All right. And now, what's going to happen to the second one? Yeah, Kim?
4 log base of A,
So 4 log base A,
and then x plus 1.
x plus 1. And that's all you can do. There is no rule for splitting apart two things that are added in the argument. Only two things that are multiplied or divided. And you do need that minus outside of a bracket. The reason is because once you split this apart, you're subtracting the whole thing that you split it up into. So it's really like that minus is distributed. Minus 3 log base ax minus 4 log base ax plus 1. You don't have to distribute the negative out. You can read it like that. But that'd be your final answer.
That is a really long one equation right there.
Yeah, it's when you combine it, it does get a lot shorter.
Yeah.
Definitely. Yep. All right, so now let's look at things that are really long like that and put them back together. So now we're going to do everything in reverse. Yeah.
In the last one, is it okay that we had x squared even though it said to not have any exponents?
Yes, because there's nothing I can do with that exponent because it's a plus 1. Where you would not be allowed to have an exponent would be if you had something like that. Now, because the entire argument is raised to a power, that 2 should be going in front. But it wasn't the entire argument, it was just a single term to a power. So there's nothing I can do about that. Okay, so let's look at this one. What's the first thing that you would do here if you were reversing everything we just did in the last problems? Yeah?
Break apart the 4 log A 3 and turn it back into log A 3 to the 4th.
Yeah, put the 4 back as the exponent. Okay, so let's start with that. Log base A of 7 plus log base A. And if you put the 4 back, what's 3 to the 4th power? Yep.
12. Or no, that's 3 times 4.
That's 3
to the
times
4th powers. 9 was 81.
81. Yep. So when we put the 4 back on as the exponent, we get 3 to the 4th, which is 81. Now we have to combine these two back together. Right? That is addition. When we recombine them, addition turns into what? Turns into multiplication. Yep. When I recombine them, I'm going to have a single log. What is going to be the base on that log? A. Aiden, is there 2 people out?
I don't know. I saw one person leave, I think, but yeah.
Yeah, you just wait for one to come back. So we got base A, and what's going to be the calculation I need to do for my argument? What times what? Yeah, 7 times 81. So that's what you get when you combine everything back together. Any question on that one? Okay. Let's try this one. I'm just going to change one of these numbers. Let's make that 71. Okay, so we have 2/3 ln 8 minus the ln of 3 to the 4th minus 71. Well, there's a few things we can simplify before we even start dealing with logarithms. What's 3 to the 4th?
81.
81. What's 81 minus 71?
10.
10. Okay, so we can just make that a 10, so we don't have to deal with that. All right. What's the next thing we would do with that first term? Oh, Kaylee, what would we do next there?
I have no idea.
So how would this 2/3 have gotten in front? Where would it have had to have been?
The power thing.
Power on what?
8.
Yeah, would have been the power on the 8. So we're going to do ln 8 to the 2/3 minus the ln of 10. All right, now 8 to the 2/3. Okay, if you need to do that out, this one, it actually comes out nice. That's the power you raise to. What you divide by is the type of root you take. And it doesn't matter the order you do them in. A lot of times doing the root first makes it smaller. Okay, so divided by 3 means what kind of root?
Cube.
Cube root. What's the cube root of 8?
2.
2. And what's 2 to the second power? 4. Yep. If you didn't want to think of it that way, you could square 8 first. What's 8 squared?
64.
64. And then what's the cube root of 64? Still 4. Yep. Okay. If it doesn't come out nice, you can always use your calculator, but that one does come out nice. All right, now we've got 2 ln's and we're subtracting them. How is that going to recombine? Well, Cole. How is that going to recombine?
The L of 4 minus the L of 10 would be the 4 times the 10.
If it was a plus, then we would have 4 times 10.
4 divided by
Right. It's going to be 4 divided by 10, which reduces to 2/5. And that's what you get when you combine all that back together. ln of 2/5. Any question on that one? All right, so that's combining back together. Now, let's go back to here. So now, I want to figure out what that is. I still don't know exactly how to type that in. But the reason that this was a problem originally was because there was a t in the exponent. We just learned that you're allowed to take exponents and move them in front, as long as you have a what in the problem. You can't just take exponents and move them in front randomly all the time. You can do it as long as you have a what. Yep. Okay, and what do you need to have an argument to what?
A power.
Okay, so we're going to have, we have a power. We're going to have a power on the argument, but what's the argument going to go to? Arguments belong to something.
A log.
A log, exactly. So if we had a logarithm involved here, we could just take that t and put it in front. Well, we can have a logarithm involved. Just take the log of both sides. Take the log of what's on the left, and take the log of what's on the right. As long as you do the same thing on both sides, that's fine. Just like taking the square root of both sides. Now, what can we do with that t? Yep.
Move it to the front.
We can move it in front of the log. So what I'm trying to show you is a different way to get t by itself, because the way that we did before works, but we still don't know how to type that in. So doing it a different way, maybe we'll get something that we can type in. Waylon, are there still 2 people out? I think Aiden's,
Yeah.
yeah, as soon as somebody comes back, then Aiden, you can go ahead, okay?
How do I cancel it?
It's fine, it'll do it, it'll fix itself. So, put the t in front, and then log 1.025. Now we don't have a t in the exponent anymore. How can I get t by itself in that equation? Because what you have now is just something equals t times something. Who cares that they're logs? Forget that they're logs. Just think of it as t times something. Yeah.
Divide by log 1.025.
Exactly. Divide by log 1.025 and log 1.025. That is what t equals. And that is another way to write what we have in that first box. Log base 1.025 of 2 is exactly the same as log 2 divided by log 1.025. They're exactly the same thing. And that is something we can type in on the calculator. So let's do it. Log 2, just make sure you close your parenthesis and divide by log 1.025. So if you look back when we graphed this problem on Tuesday, we ended up with 28.07 years. And that's exactly what we got here. Approximately. So hopefully you can see the pattern. We're going to talk more about it formally, but when you have a log that's a different base, all you have to do is take the log of the argument and divide by the log of the base. If that pattern doesn't make sense, that's fine. You can do it like this every time until we talk about it more. Take the log of each side, take the exponent, put it down in front, and then divide each side by the number that's next to your letter, and you'll have something you can type in. This is the long way to think about it. If you can go right from that box to that box directly, that's the short way. Okay. Any questions on mainly how we got this? All right. So the last thing we're going to do is purely on the calculator. So what we're going to look at on the calculator is how we can put in a set of points and find an equation that fits them. Now, in Algebra 1, you sometimes do something like that. And that's called a line of fit. You might have a set of data points, and usually by hand, you just estimate a line that goes through your data points. And you try to make it so you have as many above and as many below as you can. You try to put the line in the middle. When you do a line of fit, it's not necessarily like a calculation. It's something you drew by hand. What we're going to do is a calculation that finds the best possible fit for that data. But our data isn't going to be a line, because that's not what we're studying in Chapter 5. We're studying some things that look like this. What kind of graph does that one look like? It's not a line, yeah?
Exponential.
Yeah, it's kind of like an exponential. A curve would be a good fit for that data. So what I'm going to show you on the calculator is how to find a curve that fits that data. Now, normally you have to look at your data and figure out, is it a line or is it a curve? I'm just going to tell you it's going to be a curve. Right? We're not going to do the test to figure out if it is. And then even once it's a curve, there's lots of types of curves that this graph can do. Anything that ends in REG, those are what we call regressions. That's the process of finding a curve or a line that goes through points. It's called a regression. And there's lots of them. So we're going to look at one particular type of regression. Right? out of all of them. Okay? We're going to look at option A. And that's called a power regression. So the type, or power function, power regression, same thing. The type of formula that you're going to get is going to look like what's in that box. So an example of a final answer would be something like 3x to the 5th. I just made those up. The key is we have to use the calculator to solve for A and to solve for M. And that's what I'm going to show you how to do. You can find A and M by hand. It's just that's not something we're going to get into. We're going to find it on the calculator. I don't think, yeah, we're not going to do that part. And again, I told you we're not going to be looking at if a power model fits the data or not. I'm just going to give you a problem and tell you, use a power model to fit the data. Okay, so we're going to skip the part where you actually test the data to see if you should use a power model. Because that's actually the harder part. Trying to figure out which one of these should you even use, because there's lots of them. All right. But that's not what we're going to go through. So let's do this one. So it says determine if a power model is appropriate for the data. It will be. So we're not going to do the determine part. We're just going to find a power model for the data. So that's the directions. I'll just cross that part out. So find the power model for the data. All right, so here's your data. Well, the first thing you have to do to be able to find a power model is you have to type all of that data in. Okay. So basically, they're giving us 4 coordinates. Okay. To type that data in, if you're on the main screen, you're going to press Stat. And the first option you should see is under Edit. Option 1, it says Edit. We're going to press Edit. Now, if you go to this screen and you already have numbers in there, you can clear those numbers out. I just highlight the top one and press Delete. Just keep pressing it until they're all gone. What you don't want to do is highlight L1 and press Delete. Then that's going to delete. Okay, I'll do it, but you don't want to do this. What I just did now is I just deleted L4, which is OK because I don't need it. Now I got to do something in the calculator to fix that and get it back. Right? So don't delete the actual L at the top. So the calculator has 6 different lists you can store stuff in. We're going to use L1 and L2. So let me start writing down some of the steps. So step 1, press Stat. And go to Edit. In L1, we're going to put the X's. In L2, we're going to put the Y's. Okay, so let's start putting all those in. Okay, so L1, I have 1, and if you hit Enter, it goes down, so it's easier to do all the X's first. 1, 3, 5, 8. And now if you press the right arrow, it'll go over to L2. We've got 5, 31.2, 73.1, and 160. So when you get to step 2, you should have something that looks like that. If you don't have the same number of items in each column, that's going to be a problem, because that's like writing a coordinate and skipping an x or a y value. If you have 4 x's, you got to have 4 y's, or you don't have a whole coordinate. All right, so step 3, you're going to press Stat, and this time we're going to go to calculate. And we're going to pick option A. So go to Stat, Calc, option A. Right there. It says PWR regression. Once you highlight option A, you hit enter, and notice it defaults to using L1 for the x's and L2 for the y's. That's why I used L1 and L2. If you didn't use L1 and L2, you would need to change that now. Like let's say you used L3 and L2. I could press second 3 and now tell the calculator my x's are in L3. Mine are not. Okay, mine are in L1. Second, L1. So x is in L1, y's are in L2. Don't have to change anything. Just go down and press calculate. Okay, so calculate's highlighted. Yep.
My calculator's showing something different.
Yeah, so you're not using one of mine, so it is different.
Should
Yeah.
I just press enter?
You can. I can show you too, but you might have to do it a different way. Yeah, if you're using one that's not one of mine, it might that's going to work different. But I can still show you how to do it. So press enter, and we get these numbers. So now let's interpret what they're giving us. They're giving us an equation that's in a power model template, and they're giving us two values. Now we want to round those values appropriately, okay? Because the calculator is just doing an estimate. Based on that estimate, what do you think A should be in this problem? Yep.
5.
It's 5, yeah. So it's 5 times x. And now this decimal repeats 5 times. If it repeats that many times, we're just going to assume it would keep repeating. What is 1.6 repeating? We'll do it as a mixed number first. Yep.
1 2/3.
1 2/3. So B should really be 5/3. And that is how you find a power model for the data. This next part, you don't have to do it. I just want you to watch me do it. What was my biggest x value in the list? Biggest x value was how much? 8. Yep, so I'm going to leave it at 10. What was my biggest y value?
160.
160?
Yeah.
So let's do 175. And again, just want you to watch this. That's all I want you to do. Those, well, don't worry about that. That's from something else. Those squares you see on the screen, those are the coordinates we just typed in. Now, I'm going to type in that equation that the calculator found. In theory, that equation should go through those points pretty well. If it doesn't, then that means that equation is not a good fit for the data. Okay, well, let's look at it and tell me what you think. Does it look like the equation we found is a good fit for that data? Yeah.
How did you get the squares?
Don't worry, I'm just showing you that it's a good
Oh.
fit. You don't have to do that. I just kind of want to show you what the end result means.
Okay.
So the end result is a curve that goes through your points very well. And this data was almost perfect for a power model. All right, but all that you are responsible for knowing is how to do those 4 steps and then writing the answer. Okay. Type in your data, go to the power regression, and then press calculate, and it'll give you the answer. If you're using a different calculator, I can help you too. Any questions on that? So let me put up the homework. going to be 293, and there's a couple others that are just the combining and splitting logs. 29 through 32. So the homework is page 293, 29 to 32, and then 35, 43, 46, and 48. Okay, and don't worry if a problem says determine if a power model fits, we're not determining, we should just do it. Just find the power model. Okay, and I will put the test topics on the board in just a minute.